Hi and welcome to the video. In this one we will take a look at a simulation example that seems deceptively easy at first until you try to implement it. I'm talking about this simulation here where all we want to do is accelerate until we hit a velocity of 40 meters per second, then decelerate until we reach 30 meters per second, then accelerate again and so on. We want to be as accurate as possible to the velocity limits. Sounds easy enough, right? Well, try it yourself. As basis, you can take the vehicle simulation models used in other videos of this channel. The GitHub repos are linked in the description. We will first look at the system model and problem again briefly, before continuing with the first method, how the goal set out before can be achieved in simulation. Afterwards, I show you a second method, which allows for quicker calculation, but also leads to a slightly different result. We are comparing both methods afterwards and cover when you want to use one over the other and what the differences are. Finally, a short outlook what comes next. We have this vehicle with air resistance on it being propelled by its engine, and those are the dynamical equations of motion. Check out the second video shown on this channel if you want more detail for the model. As mentioned, we want to simulate a few acceleration and deceleration sections of our vehicle, where the point of acceleration and deceleration is based on the current velocity of the vehicle as follows. If the vehicle goes above 40 meters per second, we want to switch over to braking, so use the maximum negative power. And if the velocity goes below 30 meters per second, we want to switch over to accelerating again using the maximum power. If you haven't done so already, pause the video and actually try it. The result should look something like you see on screen right now. The tricky part is that since we don't know when this point here will actually be, we cannot do something like in last month's video where the vehicle power simply depends on time. Here, the power must change according to the current velocity of the vehicle. We cannot simply set it inside our ode function, since there is no real way to define memory. What I mean is, for a velocity of 35 meters per second, we either have to accelerate or decelerate, depending on where we were previously. So we have to solve this another way. Let's look at two methods how this can be done. In our first method, we implement it like it would be on an actual control system. What we do is the following. We call our simulation multiple times back to back, and we always simulate for exactly 1 millisecond. This time step would be the cycle time of our controller. Our each simulated interval, we first save our simulation results for later, and afterwards check our velocity and adjust the power if required. If the velocity is above 40 meters per second, we decelerate, and if it is below 30 meters per second, we accelerate. Doing it, like you see on screen here, has the effect that there is only a change if one of those limits is violated. If that happens, the power is changed, and the next, let's say 1000 calls of this function, the simulation just runs with the set input. That is until the other boundary we set is violated for the first time, and so on. Doing it like this will lead to an actual small violation of the velocity. We can see that by zooming into our plot up here. But this is what would happen on a real system with a discrete controller as well. At the start of the controller cycle back here, the velocity is not violated, so it is okay to accelerate further. When checking the next time, we are above the limit a little bit and start to decelerate. The violation is really quite small, as you can see, since not that much changes within 1 millisecond, at least for this system here. We will take a closer look at stuff like this when we look at actual controllers in some of the videos coming later in the year. Let's now shift over and look at how we could simulate this, assuming that our controller can act infinitely fast. It is not really feasible to set the time step of the simulation to something ridiculously small, because the simulation would just take forever to finish. The simulation shown previously already took around 30 seconds to complete, so we need a different method. To solve this problem, we are using event handling, and the solution I have come up looks like this here. First, we define our event handling function like this. We want to detect two events. The first one being when our velocity goes above 40, and the second when the velocity goes below 30. We want to stop our simulation in both cases, and here we set the direction where the crossing of the velocity matters. We only care for 40 to be crossed from below, and we only care about 30 being crossed coming from above, to allow for the initial acceleration to continue uninterrupted. To run the simulation with event handling, we first initialize a couple values up here, power of our system at the start, a helper variable to define our simulation end time, and two vectors to append the simulation steps to. Then we call our simulation in a while loop like you see here. When running the ode-function integrator, we only define a start and end point and interpolate our simulation result later on ourselves. The simulation runs until our event handling gets triggered. Afterwards, we define a time vector for interpolation of our results, then use Matlab's built-in deval function to interpolate our states on this time vector. You can check out my video on the ode-function integrator for more details on what happens during this interpolation. Afterwards, we set a new end time for our simulation. We do this so the time span for the simulation up here is reduced, so that we end exactly at this time after all of our simulation steps are completed. We further use this time to leave the while loop after reaching our desired simulation endpoint. Then we append our incremental simulation results of the segment that we just simulated. Finally, we set our power for the next step, and here we can use the result returned from the event handler again. Since the simulation got ended by an event that got triggered, the simulation results structure contains a variable telling us which event got triggered. For this example here, our event with index 1 got triggered around the time point of around 15.3 seconds. That was the event where our velocity reached a point of 40 meters per second up here. The way we defined it was that now we have to switch power to be negative and vice versa, as you can see here. I have also added a timer here, so we can compare our simulation time with this method with the one from the method from before. As I mentioned previously, those two methods are not identical and do not lead to the same simulation result. Which one is better for you depends on what the question you are trying to answer when running the simulation is. And be careful, because the difference is bigger than it may seem at first. Every switch in velocity and the connected inaccuracy introduces a certain error that sums up over time. You can see that here, if we run the same zoom window over the full range of our movement and compare the result of the two simulations. It is best visible if we compare the results for the first with the last positive switch. If you are interested in the exact times where those switches occur at infinitely small time resolution, you are going to need the second method with event handling. There is pretty much no way around it. But if you're more interested how it would behave on a real system, and you actually want to see the effect of a controller that can act only every 1 or 2 milliseconds, you gotta run the first simulation to get this. In the end, it really comes down to what you actually want to simulate. Or in other words, what kind of questions you want to answer with your simulation. If you want to play around with the simulations you saw in this video, there is a link to the GitHub repository with the code in the description. Okay, and that's it for this video already. I hope it was interesting and you learned something. I have decided against making a video covering Lagrange's principle for now, which was what I had originally scheduled for this month. I am more passionate about running some simulations and showing you different stuff there and how you can accomplish certain tasks, so we will do that for now. In the next video, I want to cover some basics of control theory, with a focus put on showing different concepts with the help of simulation. If you liked what you saw in this video, find it useful and interesting, consider liking it and sharing it with fellow students or colleagues that might benefit from it. Subscribe and turn on notifications to not miss any future videos. Thank you very much for watching. See you next time.